Blender has three rotation representations that we can choose from as a user: axis angle, Euler, and quaternion. Internally, Blender also uses rotation matrices. These are not directly accessible to the user, so I won't go in depth into them, but I'll briefly touch on them at the end of all of this. Of the three of these, quaternions are probably the scariest, and axis angle are probably the simplest. And because of that, I'm going to cover axis angle first, and quaternions last. So, axis angle rotations. You have an object, you specify an axis to rotate around, and an amount to rotate around it, and bam, it's rotated. Holy crap, is that simple. It takes 4 numbers, 3 for the axis, and 1 for the angle, and it couldn't be conceptually simpler. Now, I don't know about you, but when I first learned about axis angle, I thought there must be some hidden limitation in there. Surely there are orientations that you can't reach with a rotation around a single axis. As it turns out, that's not the case. You can reach any 3D orientation from any other 3D orientation with a single rotation around an axis. Or in other words, given any two orientations in 3D space, there is always an axis you can rotate around to get between them. It's pretty much the same thing as saying that given any two locations in space, there's always a straight line that can connect them. Rotations around axes are like the straight lines of the rotation path world. In fact, the similarities between straight lines and single-axis rotations go even further. Straight lines are always the shortest, most direct path between any two locations, and single-axis rotations are the shortest, most direct path between any two orientations. Crazy, huh? So in a lot of ways, axis angle rotations are kind of like simple translation vectors. In fact, the only way they could be more like translation vectors is if directly blending or interpolating between two different axis angle rotations resulted in the object rotating on an axis as well. Unfortunately, that's not the case, and you can get some slightly wonky interpolations between some axis angle rotations. It's also worth noting that it defines a very clear rotation path, a rotation around a single axis. And it's a looping path of rotation, which means that revolutions are meaningful. Hooray! However, as elegant and simple and awesome as axis angle is, I've never actually used it. If I ever have to animate an entire asteroid field, I might, but as of yet, most of the problems I've run into have been better suited to Eulers and quaternions. And therefore, let's move on to Eulers. Euler rotations are pretty much the most common rotation representation you'll see in most 3D animation packages. In a nutshell, Euler rotations are just a sequence of 3 rotations, one around each of the major axes. So, for example, you might rotate around the x-axis 20 degrees, then the y-axis 90 degrees, and then the z-axis negative 40 degrees. By rotating around the major axes one at a time, we can rotate the object into any orientation we like. And because we're just rotating around each of the 3 major axes, Euler rotations are fairly easy to grasp conceptually. Eulers also preserve revolutions around each axis, because each of the 3 rotations have a well-defined looping rotation path. However, as conceptually simple as Eulers are, in practice, they have a long laundry list of gotchas. The biggest gotcha is something called gimbal lock. But to understand gimbal lock, we first need to cover a different gotcha, which is that the meaning of the Euler axes actually change with different rotations. To better explain this, let's switch over into Blender and take a look at how Eulers work on this monkey head. In the end panel, we can see the 3 angles for rotating around each of the 3 axes. If we play with the x value, the monkey head rotates around the x-axis. Likewise, if we play around with the y value, the monkey head rotates around the y-axis. And the same with the z value and the z-axis. And if we play with the values in sequence, first x, then y, and finally the z, this behavior still holds true. However, if we now go back and play with, say, the x-axis, what the? It's not rotating on the x-axis anymore. What's up with that? The reason this happens is because we're doing rotations in sequence. Later rotations in the sequence affect the axes of the earlier rotations in the sequence. To help illustrate why this is, I've created a weird-looking device here. As you can see, we have 3 rings, each smaller than the last, with the monkey head in the middle. Each ring represents one of our Euler rotation axes. The innermost one is the x-axis, the mid-sized one is the y-axis, and the outermost one is the z-axis. Now, let's play with these axes individually. Playing with the x-axis, we can see the innermost ring rotate. Playing with the y-axis, we can see the mid-ring rotate, but notice that it's taking the innermost ring with it. Finally, playing with the z-axis, we see the outermost ring rotate, and it takes both of the inner rings with it. It turns out that this is exactly what happens with Euler rotations, and that's why the x-axis was weird earlier. If we rotate all three axes, and then play with the x-axis is no longer aligned with the world's x-axis. However, note that it is aligned with the object's local x-axis, and I'll come back to this later, but just notice it for now. Anyway, the point of all this is that the meaning, or alignment of the axes, change in Euler rotations, so it's not as straightforward as a lot of people think. And these changing axes also mean that interpolation between different orientations can be kinda wonky sometimes, which can be annoying for animators to deal with. So, that's the first gotcha. The second gotcha, which I mentioned briefly before, is a direct result of the first gotcha. It's called gimbal lock. What is gimbal lock? Gimbal lock is something that happens in 3-axis Euler rotations, where the innermost ring becomes aligned with the outermost ring. This is actually really easy to accomplish. Just rotate the mid-ring 90 degrees. When the middle axis is rotated 90 degrees like this, we have essentially lost an axis of rotation, because two of the axes are now exactly the same. This can result in some pretty strange behavior, especially with rotation interpolations, and animators generally ought to be aware of this possibility when animating, and try to avoid rotations that get close to gimbal lock. So that's the second gotcha. Now, there is one final thing you want to know about Euler rotations, and that's rotation order. You see, Euler rotations don't have to rotate on the x-axis first. You can choose any order you want to rotate around the axes. We could rotate on y, then x, then z, or z, then y, then x, or whatever. Blender has a simple way to choose this. In the rotation mode menu, you see a bunch of Euler options. The x's, y's, and z's next to each of those indicate the rotation order from left to right. So, for example, zxy Euler means an Euler rotation that rotates on the z-axis first, then the x-axis, and finally on the y-axis. This ability to choose the rotation order is actually really helpful. For example, it lets us choose which axis can create gimbal lock. Remember that the mid-ring, when rotated 90 degrees, or negative 90 degrees, or whatever, creates gimbal lock. So if we know there's an axis that will frequently hover at around 90 degrees, we probably don't want it to be the middle axis. Also, remember that I mentioned that the innermost ring stays aligned with the local axes of the object? Well, that means that if there's an axis that would be particularly convenient to stay aligned with the object's local space, you should probably make that the first axis. And similarly, if there's an axis that would be good to stay world-aligned, make it the last axis. Just remember that the first axis is like the innermost ring, and the last axis is like the outermost ring. The downside to rotation order is that it completely changes the nature of the shifting axes, which can make things even more confusing for animators. And generally speaking, that means that animators ought to be aware of these issues. A couple of final notes about Eulers. First, if you have one of the axes locked, so that you're only rotating on two of the axes, then Eulers are much better behaved. A lot of the nasty behaviors of Euler rotations, such as gimbal lock, come from rotating on all three axes. So if you only need to rotate on two axes, simply lock one of the axes, and a lot of Euler's rotation problems will disappear. Second, if you only need to rotate on a single fixed axis, like with wheels or something like that, then Euler rotations are pretty much ideal, because then it's essentially just a 2D rotation. Simply lock all but one of the axes. Anyway, so that's Eulers. They seem simple, but in fact there's a lot of complexity and potential for confusion in there, so beware. Now, finally, it's time to talk about quaternion rotations.